So we're going to look at the basics of ionic bonding. So this is a recap for the first time. So we're only looking at a GCSE level, so there are obviously bigger complexities in this, but this is the essentials. So ionic bonding is defined as the electrostatic attraction, and this is a key word they're going to look for in the exam if you're talking about what ionic bonding is or how it works. It's the electrostatic attraction between a positive ion and a negative ion. Now you have to be very careful here not to use the word atom. Atoms are uncharged, so you can't have a positive atom and a negative atom. As soon as there is a charge on it, we would call them an ion. So what are a positive ion and negative ion? Basics. Positive ions are usually, not always, but usually made from an element in group 1, 2 or 3 of the periodic table, or the transition metals. And they are positive as they lose electrons to obtain a full outer shell, which we'll talk about a little bit more in a minute. So in total they would have more protons than electrons. The number of protons doesn't change when you go from an atom to an ion, but the number of electrons does. And as electrons are negative, removing the electrons will leave excess protons, so you end up positive. A negative ion is usually made from an element in group 5, 6 or 7, the non-metals. Are negative as they gain electrons to obtain that full outer shell, which again we'll talk about when we're making negative ions. So they have more electrons than protons, so more negative particles than positive particles, so they end up negatively charged overall. Note guys, groups 1, 2, 3 and the transition metals are the metals on the periodic table, so we could say that ionic bonding involves a metal forming a positive ion and a non-metal forming a negative ion bonding together by electrostatic attraction. But the shortest sentence you could write in your GCSE exam for a definition would be the electrostatic attraction between a positive ion and a negative ion. Okay, so let's talk about positive ions first. Positive ions are often called cations because they are positive. Terrible pun, but it helps you remember. And as we said earlier, they're formed from things usually in group 1, group 2, group 3 or the transition metals. The transition metals are quite tricky to do in diagrams. They don't tend to use them in the GCSE for drawing diagrams, but they do use group 1, group 2, group 3. So let's run through what we mean by forming a positive ion. So on the left here, we have the atoms, lithium from group 1, magnesium from group 2 and aluminium from group 3. And we should know how to calculate how many protons and electrons they've got by using the atomic number of the periodic table. So lithium would have 3 protons and 3 electrons as an atom, magnesium would have 12 protons and 12 electrons as an atom, and aluminium will have 13 and 13. Obviously you could work out the neutrons from the atomic mass, but neutrons don't change. They have nothing to do with ions, so we're not going to focus on them. So when an atom is forming a positive ion, it is losing electrons to create a full outer shell. So a full outer shell, like the noble gases, group 0, have, is very stable. So this is what these metals, these atoms are aiming for. With these extra electrons that are not a full shell, so lithium would need 8 to be full there, and these would both need 8 to be full there. And they are unstable. So by losing that electron on the outside, because obviously losing will get them into the next shell in much quicker than adding 7 electrons, 6 electrons or so on, much quicker, much less energy. So group 1, group 2, group 3 always lose their outer shell electrons. So for the lithium, this would mean losing 1 electron. So 1 electron would come off the atom. It would go on to something else. That's where the negative ions come in, but they will only lose that one because lithium only wants to get to this full shell of 2. So the lithium would end up looking like this. Only 2 electrons left. The 1 electron has gone off somewhere. And the number of protons has not changed. There are still 3 protons, but there are now only 2 electrons on the lithium. So we now have 3 positive things and 2 negative things. So we have to show that lithium overall has a 1 plus charge. It's got 1 extra proton than an electron. And it has that nice full outer shell. It's like helium. It has 2 electrons in its outside shell, only 1 shell. So it is very stable now. It's a very stable lithium ion. So show ions up here. Magnesium has those 2 electrons in the outer shell. So it needs to lose both of them to a negative ion. It cannot only lose 1 because then it would not be full. It would not have that full outer shell. It would still have 1 in there, so it would still be very, very unstable. In fact, it would be more unstable with 1 in there than with 2. So it must lose both electrons. So magnesium would end up looking like this. 8 electrons in its outer shell. And its number of protons, again, does not change. It is still magnesium, so it still has 12 protons, but it now has 10 electrons. So it has 2 more positive things than it does negative things, so it would form a 2 plus ion. And it is like neon. It has that full outer shell. It now resembles neon. And similarly, aluminium, 3 electrons. It must lose all 3 of them to get that full outer shell. So it would be 3 electrons going off to join the negative ion. So aluminium would end up looking very, very similar to magnesium, in fact, because we're aiming for that same full outer shell. You're going to have the same amount of electrons on the aluminium as you do on the magnesium, because we are aiming for that full outer shell. But aluminium will have 13 protons and 10 electrons, where it's lost the 3. So it will have 3 more positive things, so it would be a 3 plus ion. When ions like this have the same number of electrons, the same number in each shell, we sometimes call them isoelectronic. So they have the same isoelectronic structure. So magnesium 2 plus and aluminium 3 plus and neon as an atom would be called isoelectronic because they have the same number of electrons. So how do our negative ions form? Sometimes we call negative ions anions. Again, terrible pun. Anions are like onions. They make you cry because they're sad, they're negative. Terrible, but it does help you remember again. So this time we're going to have a look at our group 5, 6 and 7s because they form our negative ions, and we've got the atoms nitrogen, oxygen and fluorine just to look at. So nitrogen in group 5, so 5 electrons in the outer shell. And obviously with these, it would be hard to remove 5 electrons. It would be much easier to add 3 electrons to this to go to the full outer shell. And same with group 6, adding 2 is going to be easier than removing 6. And group 7, adding 1 is going to be easier than removing 7. So these guys gain electrons to become the negative ions. And the electrons they gain come from the positive ions, and this is how ionic bonding works. So our nitrogen currently has 7 protons and 7 electrons. It has 3 gaps to fill to get to the 8 that it wants for a full outer shell. So it will gain 3 electrons. And when it gains the 3 electrons, it becomes an ion, which will look like this, same in the inside, but now 8 electrons in the outside shell. Now sometimes we show the gained electrons as a different shape, so that we can see that these 3 have come from a different source than the original ones, but you don't have to, it's not a problem. And now we have 7 protons, because protons don't change, but we have 10 electrons. Okay, note that 10 electrons, again, is like neon, so these would be similar to the positive ions we've already looked at. If we've gained 3 negative things, 7 positive, 3 negative, overall our ion would have a 3 minus charge. So group 6, same idea. Oxygen has 2 gaps to get to the 8 because it's got 6 in its outer shell. It has 8 protons, 8 electrons to begin with. So it must gain 2 electrons. So same with our with our metals, you can't lose 1 if you've got 2 on the outside. You've got to get rid of all of them. You have to get to that full shell. Oxygen can't gain 1 electron. That wouldn't be stable. So it has to gain 2 every time. Same with nitrogen, would have to gain 3. So the ion would end up looking like this, and you'll notice it is that magic. It has 10 electrons in total, like the Nobel gas. let's stay consistent and keep them as dots. So the oxygen now has 8 protons and 10 electrons, 2 negative things to 8 positive things, so we would draw it as having a 2 minus charge. And you can probably now guess what is going to happen with the group 7. We have 1 gap, we need to add that 1 electron, so we start with 9 protons, 9 electrons, we add 1 electron to it. So our fluorine ion, or our fluoride ion, we tend to name these ides, so this would be nitride, oxide, fluoride. We'll have, again, that 10 electrons, like neon, to give it that full outer shell. It's got 9 protons and 10 electrons, so it will have a 1 minus charge. Now we're at the actual bonding bit. As we said, the electrons are essentially going to be transferring from our metal, our group 1, 2, 3 section, to our non-metal. And we can't create or destroy electrons, so they're going to move from one to the other. So let's look at the first case that we've got. Note, I'm only drawing the outside shell here because that's the only shell we are changing in this. You could be asked to draw the full electronic configuration, in which case you'd have to show them like I did in the previous bits, but it's quicker to show it with just the outside shell. So we have a sodium and a chlorine. The sodium has 1 electron in its outside shell, which it needs to lose. The chlorine has 1 gap that it needs to fill to get to its 8. So logically, the sodium transfers its 1 electron to the chlorine to form a sodium ion and a chloride ion, and then they bond. The positive and the negative attraction holds them together, and you make sodium chloride. So what does this look like? Well, the sodium will lose that outside electron. Still have 11 protons, but it will now have 10 electrons, so it will be a 1 plus ion. Like all things in group 1, it would end up with a 1 plus charge because it loses 1 electrons. The chloride will have gained that electron, so it will now have 8 in its outside shell, like this. So there's our electron it has taken from the sodium. It would have 17 protons, but 18 electrons, so 1 more negative thing than positive, so it would end up with a 1 minus charge. Now, because both the 1 plus and the 1 minus are equal, that means we only need 1 of each of them. We need 1 sodium and 1 chlorine to make this work. So the formula would be NaCl, or normal salt. In a similar way, magnesium and oxygen. Magnesium's got 2 on its outside shell that it wants to lose. Oxygen has 2 gaps, so they can bond together very, very easily to form an empty magnesium outside shell. And it would then have 12 protons, but 10 electrons. So it would have a 2 plus charge, like all things in group 2. It will end up with a 2 plus charge because it's losing those 2 electrons. And the oxygen will have its 8 electrons to give it its full outer shell, 6 of its own, and the 2 that it's gained from magnesium. It has 8 protons, but 10 electrons, so we'll have a 2 minus charge, like all things in group 6. So the charges are determined by which group they're in because it tells you how many electrons they've gained or how many electrons they've lost. And again, we've got a 2 plus and a 2 minus. They cancel out perfectly, so the formula would be MgO. So far, our number of electrons and the number of gaps to be filled in our atom that's going to turn negative have matched. But what if the number of electrons does not match? Obviously, the world is not made only of group 1 with group 7, group 2 with group 6. You can have a group 1 thing react with a group 6 thing, or a group 2 thing react with a group 7 thing. So how does that work? How do we make that work? When we said, obviously, the oxygen has to gain 2 electrons, or it's not got that full outer shell, but sodium only has 1 to give. Now, there are 2 ways to think about this. Either it can be quite obvious that sodium has 1 electron there, oxygen has 2 gaps, so we're going to need 2 of the sodiums, okay, giving 1 electron each to make the oxygen full, so 2 sodiums to 1 oxygen. The other way we can do it is work out what charges those ions are going to have, and that gives us a guideline. So if we remember, our sodium we know is going to lose 1 electron, so our sodium is going to become a 1 plus ion, because it will have 11 protons but only 10 electrons. And our oxygen is, that's not the easiest way to draw that, let's get rid of it. Our oxygen is going to have its 8 electrons on the outside because it's got to have that full outer shell. It can't only have 1 electron on it, so it needs 2 to have come from a sodium. It's going to have 8 protons, 10 electrons, so it's going to have a 2 minus charge. Now obviously these charges don't match, 1 plus and 2 minus, they don't add up to 0. But what we can do, like we worked out over here, if we had 2 of these, it could fit up. That 2 there, not matched by a 2 there, tells us we must need 2 sodiums. And the 1 means we only need 1 oxygen. So we can swap the charges to tell us the number of the atom that we need in the beginning to form the number of ions. So now we have 2 Na ions, 1 plus each, adding up to 2 plus, and 1 oxygen ion with a 2 minus charge. And that just tells us what our formula ends up being. It means we need 2 sodiums for 1 oxygen, so our formula would be Na2O for our sodium oxide. And this works with all of your ions. So if we did magnesium and chlorine, like we did last time, magnesium's got to lose its 2 electrons to get to that full shell. Chlorine only has 1 gap. So our magnesium, as we know, is going to form a 2 plus ion because it will end up with 12 protons but only 10 electrons. It has to lose both of those electrons. Our chlorine, when it becomes its chloride, can only gain 1 of them though. It's only got 1 space. It can't have 9 electrons in that shell. It can only have 8. It can't put it in the next shell out because then it wouldn't have a full outer shell. So our chloride is still going to be 17 protons, 18 electrons. So it will have a 1 minus charge. And again, we can look at the charges and go, okay, there's a 2 this side, but only a 1 this side. That must mean I need 2 of these. So I need 2 chlorines at the beginning to make my 2 chlorides. So my formula will be MgCl2 because I need 2 chlorides for every magnesium. And all ionic compounds would work like this. So aluminium with its 3 electrons and chlorine with its 1 gap, you would end up with a 3 plus and a 1 minus. You would need 3 chlorides to match the aluminium 3 plus. So you can always use the charges to work out how many of the other ion you need. But remember, like we saw on the last page, if they match 1 plus 2 plus 2 minus, you only need 1 of each of them because they already cancel out. So you don't need 2 oxygens, 2 magnesiums because they cancel down to 1 and 1. A reminder to sum up that if you are describing ionic bonding, if you are defining ionic bonding, if you are trying to say how ionic bonding works, the simplest sentence to use is the electrostatic attraction between a positive ion and a negative ion, and then use the diagrams for specific examples.